Welcome to part 2 of Foundational Concepts in Semantic Modeling. This part will deal with logic. Logic is the second pillar of semantic modeling, set theory being the first. And we'll talk about a couple of types of logic that are important to our semantic modeling development. The first kind of logic of interest is propositional logic. Definition. A proposition is a statement which can be either true or false. So for example, if I say it is raining, meaning it is raining here now, then presumably that statement is either true or false. So that would be a proposition. In propositional logic, a proposition is often represented by a letter. P or Q are often used. And so if I say the proposition P or the proposition Q, that's a common usage. There are 5 logical operators in propositional logic that can generate additional propositions, and we're going to talk about each one of them, and each of them are very important to understand. The first one is conjunction. Conjunction is often represented with a caret or an ampersand or the word and the word and is the way that we'll represent it in our controlled English. So for example, consider these propositions. Given P is true and Q is false, what is P and Q? Well, the answer is false, because in conjunction, in order for the conjunction to be true, both of the operands must be true. Both P and Q would have to be true for P and Q to be true. Or given that P is true and Q is true, what is P and Q? The answer is still true. The answer is true. Now both P and Q are true, so therefore the conjunction is true. The next operation is called disjunction. It's represented with a lowercase v, or maybe you want to think of it as an upside down caret, sometimes a vertical bar, or the English word or. Example or question, given P is true and Q is false, what is P or Q? And the answer is true, because in disjunction only one of the operands needs to be true for the disjunction to be true. Given that P is true and Q is true, what is P or Q? Well, it's still true. If either one is true, then the conjunction is true. And if they're both true, then it's still true. The third operation is implication, often represented with a right-facing arrow, sometimes written as implies, and this symbol is usually spoken as implies. And in our controlled English representation, we will use if, whatever, then. So if some condition, then some implication. Examples, given P is true, if P then Q, what can you say about Q? Well, you can say that Q is true. If you have this implication is known, if P then Q, and you know that P is true, then you can say that Q is true. Given Q is true, and the implication if P then Q, what can you say about P? The answer is nothing. There is no reverse implication, if you will. The next operation is necessary and sufficient conditions. This is represented as a bidirectional arrow, and it's spoken in English as if and only if. So, given P is true, and given the necessary and sufficient condition P if and only if Q, what can you say about Q? Well, you can say that Q is true. Given Q is true, and the necessary and sufficient condition P if and only if Q, what can you say about P? You can say that P is true. In other words, the implication works in both directions, as is suggested by the bidirectional arrow. The fifth and final operator is negation, sometimes written as this little sideways L or angle, and represented by the English word not, which is what we will use in our controlled English. So given P is true, what is not P? Not P is false. Given that P is true, what is not P? It's true, because not P is false and not of the false is true. So not just changes a false into a true and a true into a false. That is the end of propositional logic. Now let's talk about predicate logic, also known as first-order logic. Predicate logic is important because it allows a representation of the contents of a preposition. In propositional logic, it's just a proposition is a unit. It's either true or false. You can't look in it. You can't represent the inside of it. Definition. A predicate is a symbol which takes arguments and returns true or false. That should be or. The number of arguments is called the arity of the predicate. Predicates with arity 1 can be used to represent class membership. So I could say, referring to our previous models, President of USA as a predicate with argument George Washington means that George Washington is a member of the President of USA class. Predicates with arity 2 can represent binary relationships between things. So for example, if I have the predicate wife, arity 2, it might take the argument George Washington and Martha Dandridge, and that would say that there's a binary relationship named wife between George Washington and Martha Dandridge, or in other words, George Washington has a wife relationship with Martha Dandridge. Predicates with arity 2 can also represent characteristics or data about something. So imagine, for example, the predicate date of birth. It takes two arguments, the first being the subject and the second being a date. So date of birth of George Washington is the 22nd of February 1732. This is an example of predicates used to express data about a subject. Predicates with arity 1 can be transformed into predicates with arity 2. So whereas I can write President of USA of George Washington, an arity 1 predicate, I could rewrite this with the is a predicate. Is a, first argument George Washington, second argument President of USA. So the is a predicate takes an individual and a class as arguments 1 and 2, indicating that the individual belongs to the class. Models with only arity 2 predicates, that is, all of the predicates in the model are arity 2, are directed mathematical graphs or digraphs, and they can be so visualized. So consider this visual graph. We have the concept George Washington. We have an is-a relationship with President of USA, meaning that George Washington belongs to that class. We have a date of birth predicate with the value 22 February 1732 and a wife predicate with the value Martha Dandridge. So each arity 2 predicate forms what is called a triple with a subject, a predicate, and an object. And so what is written in predicate logic as predicate of subject-object is equivalent to the triple representation of subject-predicate-object as a threesome, as a tuple, if you will. Or wife, George Washington, Martha Dandridge is equivalent to saying subject, George Washington, predicate, wife, object, Martha Dandridge. We will often refer to a predicate in our modeling efforts as a property. One additional definition, a function is a symbol that takes 0 or more arguments and returns another non-logical symbol. By non-logical symbol, we mean not true, not false, and not one of the 5 logical operators. We'll talk more about functions later in this set of slides. So that's the conclusion of our discussion of propositional logic and predicate logic. Now for an exercise to test your comprehension of this material. Your problem is to create a model which is equivalent to this visual graph. Looking at this graph for a moment, I think we're going to start with the person class. All of the arrows are coming into it. It seems like a good place to begin. So let's create a new file. We're going to start from scratch this time, and we'll call it logic1.sadl. And we're going to notice using content assist, if there's no space put in automatically, I might need to add a space before I do the content assist. So we're going to start by saying that person is a class. Now, we have President of USA, and this is a subclass of person. That's why we kind of started with person. And we have date of birth is a predicate, or in other words, a property. And wife is also a predicate, that is a property. Okay, given this, we can now say that George Washington is a President of USA, and we can combine some additional things here. So that's one triple, if you will, from a graph point of view. We can also say that George Washington has date of birth and give his date of birth 22 February 1732. I could end there, and in fact the width is just syntactic sugar to make it look better or read better in English. We don't need it there. But I can go ahead and add my, with or without a comma, it doesn't matter. I can add my third triple with wife, Martha Dandridge. So now Martha Dandridge is not defined. So I need to define Martha Dandridge, and going back and looking at my graph, I see that Martha Dandridge is a member of the person class. So that kind of completes my model. I've represented all of the triples that are shown in the subject graph. Notice that I've got some warning messages here. These have to do with some things that are missing from the model that might be useful, and we'll get into those in part 3 of this tutorial. So that's the solution to the exercise. There are a couple of things that are worth noting in this solution to the exercise. First of all, you'll note that although we are defining things in a sequential manner here, it is possible to reference a concept, Martha Dandridge, an individual in this case, before that concept is defined. So, continue on with our discussion of predicate logic or first order logic. Let's talk about quantification. So quantifiers bind variables to non-variable symbols, and we'll see examples of what that means in a moment. Quantifiers allow us to make statements about multiple things declaratively, and there are two quantifiers that are defined in predicate logic. The first quantifier that we'll talk about is the existential quantifier. It is represented with the symbol basically a capital E turned backwards, and it is read as there exists. So for example, this says there exists X such that X is a person, and X loves logic. So we read that there exists X such that X is a person and X loves logic. But represented in predicate logic, person of X is a predicate with arity 1. Loves is a predicate with arity 2. And whatever X is, that is, we already said there exists some X, so whatever X is, this person, X is the first argument to loves, and logic is the second argument. Existential quantification. We might say in English, someone loves logic, or there's someone who loves logic. In other words, there exists. Existential quantification. The other quantifier is the universal quantifier. The symbol is an upside down capital A, and it is read for all. So for example, for all X, rich person of X implies loves X money. Or in other words, for all X, if X is a rich person, then X loves money. Remember that we have the implication operator from propositional logic. So this says for every X where X belongs to the class rich person, there is this relationship between X and money, that X loves money. And we might say in English, all rich people love money. So let's look at an example with multiple quantifiers. So this reads, there exists X such that X is a man, and for all Y, man of Y implies shaves of XY, if and only if, not shaves YY. So you might say in English, there is a man who shaves all and only men who do not shave themselves. So this example is actually a very famous paradox called the Barber paradox. And why is it a paradox? There's a link on the slides. You can look that up. But fundamentally, it's a paradox because we have an implication here that there is some man, that would be the barber. There exists some barber, and for every man who doesn't shave himself, the barber shaves him. So what about the barber? So the barber is also a man, and if the barber doesn't shave himself, then he must be shaved by the barber, but that would mean that he shaves himself, which would violate the constraint. So you can see that it is a paradox from the point of view of how the barber fits into this particular expression. So that's the end of our discussion of predicate logic, end of part 2 of the tutorial, the foundational concepts in semantic modeling tutorial. The next part is part 3.